Recording in progress.
Hello, and welcome back to Lecture 3 of Quantum Information Science, Physics 116, where we'll continue our discussion of the kinematics of probability theory. So far, we've been giving the idea of thinking about quantum information starting from probability first. If you don't like the concept of starting with quantum mechanics with probability first, then perhaps the fact that this course is quantum information science. The information part of that information science really requires us also to bring in probability in a way that will allow us to treat things sophisticatedly. So we began with probability, and just to give a recap of where we were last time, we started off thinking about what the conditions were for the density matrix, or for the probability density vector, P here. So a probability density vector. We even talked about terminology of the probability density vector and what the three conditions were. It needs to be normalized, the values need to be real, and they need to be greater than or equal to 0. So what we're going to do today, so what we did last time is thought about the interpretations. We discussed what the consequences of transformations were. We were able to discuss the change of basis transformation. For us, this was just an active or a passive permutation. It's just changing the elements. It doesn't actually change any of the numbers. And if we want to think about transformations that actually did something a little less trivial, we thought of the stochastic change of basis, where we had convex combination of permutation matrices. I'll say a little bit more about what it means to be a convex combination in a moment. And then the outline for today is to continue with our discussion of bistochastic matrices and then go into transformations in general. Once we have transformations in general, we'll be able to look at differential changes in probability vectors. That's our plan for today. And then next week, we'll mirror all of this discussion. The only thing we'll do is change each one of these probability density vectors into probability density matrices. And we'll actually walk through the same exact machinery, lift all the things that we understood of the probability density vector and apply them to our quantum states. Just recapping a bit of our discussion from last time, I wanted to give perhaps another way of thinking of bistochastic matrices. So our bistochastic matrices we thought of as a convex combination of permutation matrices. What does it mean to be a convex combination? Let me add a note here. So convex combination is a conic combination which is a combination of entries, say X, with CI greater than 0. Think of this, and thank you, Brent, for elucidating. Think of this as some set of points. We pick all the lines starting from the origin through those points and define some sort of cone. We take the outside of this bundle. So that's the main idea if we think of this as a set of points or lines. And so that's our conic intersection. We could also have what's called an affine combination. This is where we have CI, XI, with sum over CI equals 1. So convex combination is both. Affine and conic combination. The main reason to introduce this terminology is that when you read the literature on quantum density matrices, quite often you'll hear this discussion of convex combinations. If you go and look at the literature on optimization, you find a fantastic book called Convex Optimization, and a fantastic course called Convex Optimization. in there, they're thinking all about convex combinations and convex sets and thinking about optimizing over convex spaces. So when you have a set where I can take one point and the other point, I can always connect a line that remains in the set. And that's pose as a instead here, we'd have this point and this point where a line between them would go outside of the set. So in any case, this is our discussion of convex combinations, but this is also essentially what we have in probability theory, that we have some sum over C, J, Ci sums up to 1, and Ci is greater than 0. Okay, so that's why the terminology convex combination. Okay. Yes, and so returning to our main point here about bistochastic matrices, the way that we introduced this last time was saying that if we think of quantum, if we think of a probability vector, P, and this vector needs to be normalized to 1, and all the entries have to be real and positive. If we took instead the complex, the transpose of that vector, and that were also equal to 1, then this would also satisfy all 3 conditions: normalization, reality, and positivity. Okay. So because both of these work, we could set up a probability theory, the structure of it, by having these matrices either multiply all the vectors on the right, then this should be a valid probability function, a vector. Right. And if we, instead on the other side, P prime, it's left stochastic. We will exclusively deal with column vectors. So in this lectures. Column vectors. I think that's enough caveats on bistochastic transformations. You can also think that if a matrix is bistochastic, if it's both, you can also think that that means that if we're considering, as in our course, only right stochastic matrices, then that would say that if M is bistochastic, then if M is bistochastic, then we could also imagine that we take the transpose, and transpose acting on double prime, because it's another vector, is valid probability vector, then M is bistochastic. A little bit of overkill, but nonetheless, that's the characterization we had from last lecture. We're thinking about these bistochastic transformations, and we thought of them as convex combinations of permutation matrices. Now, if we want to think about the most general setting, as I mentioned, this convex combination is not the most general case. Instead, what we can do is think about the case where we don't enforce anything about the structure of these matrices and instead think about just transitions. In fact, we can recover ordinary matrix multiplication by thinking about transition matrices. And so we'll introduce this notion of transition matrices and allow us to introduce a little bit of standard terminology that if you haven't seen it, or if you have, it'll be a good refresher. So first, let's introduce some of the basic ideas from Markov matrices, Markov chains, all these different notions of probability theory. We're going to call them up first. We're going to write it down in the following way. So here X, this capital X is supposed to represent a random variable. The random variable can realize several different outcomes. And here we're saying that if the n-1 variable in some list of variables has the outcome probability of j, whatever j might mean, then the next, what is the probability that the next item in that list has outcome I? And so this is a conditional probability. So let's define the conditional probability as follows. So it's the probability that xn is equal to I and xn minus 1 is equal to j, divided by the probability that xn minus 1 is equal to j. This we can also write down as the following two ways. We'll write down P of I coming from j. Or we could write this down as P j goes to I. These are all the same idea. And this is the notion that in each one of these different x1, x2, xn, these are different samples from a series of samples. So a series of samples might be samples from random walk. It might be samples of different weather conditions. It could be all sorts of things. But the idea is that it's transitioning from one event to the other. With this definition here, we can organize things into a matrix form. And so if we give our most general transition matrix, stochastic matrix, write down Mij, we'll just summarize all these things inside of red, and we'll pick one. So we'll pick P I goes to J. This is consistent with our discussion before that we want everything to act as if they were column vectors. So if we have some initial probability density, probability vector, we multiply the probability that things are at site I, and then they go to site J, and then we'll just sum over J. And this will give us some new probability. And this probability would be at site I, because we're summing over all the different initial values that were at site J for all the different J's, and we're thinking about how they've moved into I. So just from this definition alone, so we pick this definition and just try and take note, or otherwise remember that we've chosen this form and not the other. The other would be if we picked left stochastic matrices rather than right stochastic matrices. So still our condition here is going to be important that we take this and remember here that if this is the probability of j going to I, sum over I, then this has to be equal to 1, just from the way that we've defined this as transition probabilities. This is saying that if you start out at j, you have to go somewhere. You have to transition to some I. So this is because it's transition probabilities. So the equivalent way of saying this is that Mij, sum over I is equal to 1. And this is the most general stochastic matrix that I can think of. Okay. So now for Markov matrices, you think this Markov matrix is just a way of organizing all of the different ways that you can make these transitions into a matrix format. So concrete example, let us take some expressions here. We have some site, another site, maybe one more, and we'll just make up some graphs. It's not particularly important what it is, but we'll take, let's say, some We'll call this maybe 3, 2, 1. We'll have some transition. 1 to 2, 2 to 1, 2 to 2. Probability 2 goes to 2. Probability 3 goes to 3. Probability 1 goes to 2. Probability 2 goes to 1. Okay. There's some Markov matrix. The way that we can think of this is that we can organize things. If you like being organized, and you want to think about how to just arrange these things. Even if you've never seen probability theory, if we organize things correctly, then we can just actually see it show up quite nicely. We have some probabilities here. And then if we want to know what happens after we apply this Markov transition matrix to get out, we can just think about what matrix we need to multiply, and not so much even the matrix, but actually the definition alone would give us a very good insight as to how to organize things. So we take P1 coming from K, just as we discussed in the previous setting. Okay, PK. Okay, so if we think about how we can organize this nicely, we can put down P1 goes to 1, P2, 1 from 3. Then we continue. 2, P, 3, 3, P, 3, etc. That'll give us the correct output. So this is just one way you can think of what a Markov transition matrix is, and matrix multiplication. Okay, these things are all just fine. Okay, I would pause here and ask for questions, but this is just online and being recorded. We got a few interesting questions in class about whether or not the concept of bistochastic was connected to detailed balance. Detailed balance is a condition about equilibrium, and we'll talk a little bit about long-term behavior when we get to the end of this lecture. So that's our 10th question. Okay, the next thing that we want to think about is differential changes of the probability So we think of a probability density vector, we can think of how it changes. And if we want to get out a differential equation that will govern those changes, and even the structure of a differential equation that would govern those changes, let us start with just thinking about how to compute what the changes are inside of a probability density vector. So we take the kth component, expand, say J. So we're going to think of this as the change component. So this is change of component. This is transitions in and transitions out. Our transitions in will be all of the things that transferred to J from the previous step. And the minus all the things that were at J and wherever they went to. Okay. Now that the indices for summation are going to be important to us to make sure that we keep track of everything correctly. Okay, so now we can bullet this equation a little bit. And what we're going to do is try and get perhaps a little bit of a simpler form. We'll be able to pull out a few more things that will make this interesting. And we'll connect into how we might think of this in other situations. So first, let's simplify a bit. We'll simplify using the following trick. So now we're going to do sum over I Mij. But now we want everything to be in terms of the same variable. So I'm just going to write down delta jk. I'll put down a pk, the sum over k. Nothing too cheap. Now we can pull out the k, we can pull out the pk. And this is our transition. This is the change in a single component due to the transitions in and transitions out. A beautiful reference in all these things is Van Kampen's book, Stochastic Processes. It's a very nice introduction. I really enjoyed reading it, and I hope that what we have helps supplement that. We're not quite done with our equations. Let's continue our derivation here. It's not quite a differential equation yet. This is just some amount of change. And we're going to take a second here to think about how this is related to rates. So M is the probability of transitioning from K, MJK, this one, this particular variable here, is the probability of transitioning into K, into J from K. That's what's written. If we want to think about what the rate is, the rate's different than the transition. We need to think about how this changes in time. So we do delta Pj over delta T, Mjk over delta T minus sum over I, Mij. Now we can define a few things. First, let me highlight here that this term here we've kept around, but this term in principle should be 0, or not 0, should be 1. This is our condition for a stochastic matrix. So we didn't enforce it here because it would be better not to, not yet, because when we get to this step, give this another color. These terms we're going to write down as a rate. So write down Wjk is equal to Mjk over delta T. Now, we need to choose delta T appropriately. So this should be large compared to M. And small compared to the time evolution. So some examples of this might be you have some large object inside of the ocean or inside of a gas, and it's being hit many small times. And every time it's hit, it gets some stochastic change inside of what direction it's moving. You can imagine that being a transition from one direction to the other. That would be described by MJK if it's a probability of transitioning. And it would be described by WJK if it's the rate of transitioning. So just to be a little more pedantic here, rates, quantities per second, per time. And here, W is going to be probability per time. premises. So that's our rate. And then we can plug this into this overall equation. And before we do so, let me take one further step to define one more thing that will be useful for your repertoire of information. This quantity, sum over W, JK, sum over J. This is the degree or the out degree in this particular case. This is the weight of all of the transition rates out of site event K. So this is the degree. In the degree matrix, D JK is equal to delta JK DK. Okay, it's a lot of defining of things. Now we should be in a good position to write down our master equation. Sum over K, good W JK minus D JK PK. This is our master equation. So called because so many important results have been derived from it. Yeah, no other reason, as far as I can tell anyways. Okay. All right, so with this equation in hand, we can proceed a little bit further and actually see a few more things that'll be interesting. And the next thing we want to see is how to actually get out continuous time evolution. So we're going to simplify things with rather standard notation. We're going to call L W minus D. We're going to think about what happens when we have our differential equation, P dt is equal to L times P. So we can do this relatively, I would say definitely not a rigorous derivation, but a nice derivation that you can use over and over again in many instances, as long as L's time independent, or if it's time dependent and commutes with itself at various times, then we can do the following use of notation. I want to say abuse, because it's actually a very nice derivation. So again, we assumed L is time independent, so we can just integrate both sides. This gives us an L times T. The other side, we get log of P, evaluated from 0 to F. So it gives us log PT minus log P0 is equal to LT. Take the exponential of both sides, we end up e to the LT times log PT Okay, remembering our properties of exponentials, these things cancel with the log. We're also able to divide through or multiply through such that we get e to the LT times P0. This is our continuous time evolution. It's worthwhile just to remind everyone how we should be thinking of exponentials of matrices. We should also point out here that this m of t that we've defined using L is valid for all t. It will always remain a probability transition matrix. Okay. The conditions that we need L to satisfy are that it's of the form W minus D. This actually implies that the sum implies that one of the sums is 0. So what we're going to actually not belabor this point, but the derivation is going to be important because we'll see something similar. And I should highlight here, I think we got a question in class about whether or not this was like the Schrodinger equation. This is not like the Schrodinger equation for a number of reasons. First off, there's no imaginary unit here. Also, which means that this converges to a fixed point rather than, or a fixed point oscillates between some subspace, and that subspace may be very large, but nonetheless, it will converge to something. Whether that something is an orbit or not, it will still converge. This is all connected to ideas of detailed balance, ideas of ergodicity, and yes, and many other things, thermalization. These are all connected ideas. So yeah, that's what I wanted to say about these graph Laplacians, these quantum walks, these Markov chains, all these different ideas, but these are all from the notions of probability. And just to remind us one more time that we don't lose sight of the bigger picture, pk still equal to E hat k times p. So this definition hasn't gone away, but note that whenever we use pk, we are assuming that we have some big fixed basis of discourse, which is what we'll turn to much more next week. Okay. So with that, we've reached a very nice stopping point, but we're not going to end here. We have a little bit time left. And so what I want to highlight here is that this is our summary of the kinematics of probability theory. It's obviously much more. There were some questions also asked about statistics. So if we want to know questions about statistics, such as rather than what the probability is, we want to answer some questions about that probability, the probability vector, and inferences that we can draw from that probability vector, and inferences we should take from that probability vector. So we're not going to do statistics. It's just not where we're going to be at in this class. However, the lab will include some statistical aspects of probability where you'll be asked to estimate some properties of bits and of qubits. So what we're going to do next is a kinematics of the bit. And we're going to do it following the same exact route that we had before. We'll do kinematics, or constraints rather. And we'll do interpretation. Change of basis. Stochastic change of basis. And then finally, we'll look at time dependent. This will all be preparation, I think, quite obviously, for what we think of. We think of qubits. Kinematics of a bit. Okay. So first thing is just the constraints. It's easy enough to articulate. We have P being a number, a real number between 0 and 1. And then we can write this down as a vector. We have P and 1 minus P. Then 2, we can interpret this vector. I'm not going to say anything too technical about the interpretation of it. Rather, what I'd like to do is just highlight some of the ways that you might intuitively think about interpreting a two-outcome situation. Hopefully it's suggestive enough that you might think of some questions or some instances that this might come up. You're having a baby. You want to know, is it a boy or a girl? You're running for office or playing a game. You want to know, did you win or lose? And with what probability? Maybe you're at the casino and you're playing roulette. The question is red or black. Could be a coin flip, heads, tails. could be 1 and 2 instead of 0 and 1 if you're like MATLAB instead of Mathematica, or MATLAB instead of Python, rather. I'm actually not sure what Mathematica counts by. Okay, so that's our interpretation, part of it. This is just there's many different ways we can think of a bit, what a bit might be, whether it's a computational unit, whether it's a question you're asking, whether it's an outcome of an event, whether it's something you're going to repeatedly do. And when you think about this case that you're repeatedly doing something, and this will bring us to a piece of terminology that's worth bringing up to kind of highlight the main idea of both quantum and experiments using a bit. So when we get to the lab, we're going to talk about IID, which is independently, identically distributed distributed things. So in this case, we're doing the trials where we're going to test out a single bit. We'll test out this bit over and over again. So I think some of the more appropriate examples for IID would be if you had a coin flip, if you were playing roulette, perhaps if you're, yeah, actually that's not a great one. So heads or tails, playing some roulette game, or maybe repeating some computational experiment multiple times, thinking about a quantum situation that we'll discuss in the context of using Amazon Bracket. And so in the case that we repeat these things many times, there's a terminology that will be useful for us when we get to the lab, which is this notion of a task, which prepares the situation described by P, or prepares P depending on what philosophical outlook you're looking at. And there's shots of the task. This notion of shots is just repeating that task many times and recording the results. Okay, so when you do these tasks and you repeat them and you get all these shots, each one of the shots is IID. Assuming there's no drift or something strange. Okay. The next thing I would like to highlight is a conceptual, is that if we think of this situation here with our bit having a probability between 0 and 1, then we can label we can label our two outcomes. And we connect them with the line. I'm going to be a little suggestive here about next week when we get to the bit. So we're going to then draw our line. We'll have this line drawn going from the north to the south. What we're going to have here is this line's coming through this sphere. And this line's representing the probability of getting outcome 0, outcome 1, if we measure from the origin at 0, or at the bottom of the sphere. If, however, you like your coordinate systems for spheres centered at the center of the sphere, what we have instead is thinking about how far up or down this line you are from the origin. So you're here, for instance. In the case of the blue mark, which is small, this blue line goes from -1/2 to -1/2. The blue vector is the bias. I spelled this wrong. The bias. So the bias is the probability minus 1/2, and this is bounded between positive 1/2 and negative 1/2. It's a quick thought question here. Think about why the bias can be positive or negative. It's also a very interesting time to pause to think about negative numbers showing up inside of our discussion before we have anything to discuss with quantum mechanics. The negative numbers are here showing up because you can be biased towards or you can be biased against some outcome. And so if you're biased against 0, then you have a negative 1/2 bias. And that would be that you're completely biased against 0 and all the outcomes are coming out 1 and you don't see any outcomes 0. Okay, so it's a couple different ways of thinking about this. This would be the bias. And then in black, it's the probability. That'll be important to think about as we move forward. Okay, so now we can think about the kinematics of transforming a bit. This will get us to see a few of the things that we've discussed so far illustrated. So first, we can think about the change of basis, the stochastic change of basis, and general stochastic transforms. Change of basis, in the case of a single bit, well, we only have one permutation we can execute, or two permutations we can execute. We have the swap, X, permute, gate, the not gate, a lot of different terms for this. We'll see some of the other ones as we get further into the course, but right now it's just a permutation gate, a permutation action, a permutation matrix. All the words mean roughly the same idea. So we have this one, and we have one more. It's the trivial one. So then the stochastic transformation, so we just take some W, which will be a probability between 0 and 1, take P 1, 2, plus 1 minus W identity. So the nice thing is that we can actually see almost immediately, maybe we have to write it out, we can see that this matrix is symmetric. Symmetric, that means M equals to M transpose. This gives another look of what it means to be bistochastic. So bistochastic change of basis, or stochastic change of basis is doing the change of basis with some probability, and what results is a bistochastic transformation. Okay, and then our general stochastic transforms, the only conditions that we need are that the columns add up to 1. So we can pick for each column an independent number, W1 minus W1, and we'll take W2, 1 minus W2. So this is these are three different examples of how you might think of M matrices from any one of these classes. Okay, let me also note, important, but maybe somewhat obvious, but also important to write down, these W1, W2, and they're all bounded between 1 and 0. Okay, it's important to write down these W's are bounded because our next look will be the case where W is not bounded, and it won't be bounded for the transition matrix because we don't know how much transition over what amount of time. So if the amount of time gets really, really small, or the amount of stuff that got transitioned is really, really large, then we end up with the different corresponding cases. So we take our general case for a transition matrix, W1, 1 minus W1, W2, 1 minus W2. L is going to equal to W minus D. W is almost completely arbitrary. So remember, we said that W needs to satisfy a few conditions. And the few conditions that it needs to satisfy are just that W21 and W12 are just greater than 0. That's greater than or equal to 0. As long as these numbers are greater than or equal to 0, it actually doesn't matter what's on the diagonal. What's on the diagonal will be positive or negative. The reason that it doesn't matter is that the diagonal will be corrected or fixed or transformed according to the sum along each row. So one nice thing is that you can hopefully spot that the conditions on L are that the rows need to add up to 0. So last point here, so we take e to the LT times p is equal to p prime. Okay, so with that, we're just about out of time. And so I won't say, I think there's not much more to say. So what I'd like to end today's lecture with is just a little preview of what we're going to see next week. So the preview of quantum theory. So we've gone through a lot of machinery, a lot of mechanics, thought about how to derive master equations, how to get at Markov transition matrices, how to get at bistochastic transition matrices. We discussed the change of basis formula. So what we're going to do next time is just take this probability vector and we're going to lift it to quantum theory. And we'll do so with the following operation, which is called diag. Those of you who have programmed in any language, almost any language that uses linear algebra, you will have seen this command, which takes the entries of a vector and puts them along the diagonal of a matrix. So this matrix that we put along this diagonal is a valid density matrix, a valid quantum state, a valid quantum density matrix, and that we can actually carry through all the machineries that we have so far on this row, which I guess we'll call just in solidarity with commonplace notation for diagonal matrices inside of linear algebra, we'll call it some lambda. And this lambda, this capital lambda, is a valid density matrix, a valid quantum probability density matrix. And so we can actually go through and carry out all the machinery that we did so far and actually see exactly how it lines up with quantum theory. In the case we actually started off with a quantum state of this form. So that's where we're going. We'll retread our steps, introduce more concepts. We'll get out unitary evolution. We'll get out dissipative quantum evolutions, and we'll think about quantum channels, think about what are allowable quantum channels. And yeah, that'll get us into a few ideas of decoherence, and that'll be close to wrapping up the second week of the class. Okay, so I hope everyone's enjoying the lecture series so far. And I look forward to talking to you again on Monday. So have a good weekend.